And okay.
And I look, yeah.
Have a good class.
You too. Thank you.
And feel free to call me later. I'm at work.
Oh, I might. I'm okay. Cool.
All right.
Cool. Hello. Sorry. Hello. Okay. Hello. Oh, you can't hear me, or I can't hear you. You probably can't hear me, and I can't hear you. Sorry. Hold on. Okay. Wait. Oh, good afternoon. All right. Yes. Can people hear me though? Actually, I don't know if I can hear
Yes,
you. You can. Okay, thank you. And that totally. Thank you.
Yeah, we could hear you, Professor.
Thank you. And thank you, Shomari. And that totally counts as points. That's 75 points right there. Okay. Oh wait, I'm letting more people in. Wait, I'm trying to let more people in. Yes. Okay. Okay. Oh, and I'm turning this down. Sorry. You'd think. Okay. Yes. Good afternoon, David. Hi, and good afternoon, Jitlali. Good afternoon, Noelia. Good afternoon, Avery Yeller. Good afternoon, Liani. Good afternoon, Shamari. Good evening. Sorry, Shamari. And thank you for telling me that you could hear me, David Wallace. Oh, and that also counts. That counts as something. That counts as closing a conversation or whatever, even I think you've already done that one. But yes. Oh, and yes, that count. Thank you, Jitlali. That counts as closing a conversation or as being a human being. Good afternoon, Michelle. Oh, more people coming. Sorry, hold on. Okay. Oh, and yes, and thank you, Noelia, and thank you, Michelle, for telling me that. That is helpful. Good afternoon, and it counts as points. Good afternoon, Tomika, and thank you for the yes, and good afternoon, Shankia, and good afternoon, Juanita. Good afternoon, Hoyin, if I'm saying it right, which I'm still not totally sure. Good morning, Jean-Pierre. Good afternoon, Janine. Oh, and by the way, this whole thing of like whether it's afternoon or morning or evening, one of the reasons I never correct anybody with that, besides the fact that I'm always spaced out and don't know. Oh, and good. Oh, that's nice. She actually directed it to everybody. That's so like community-ish. Yes. Good afternoon, Catherine and everyone. And the reason I'll never correct anybody on the time thing, like when you say good morning or good afternoon, A, like I don't really know half the time, but B, also, you could be zooming in from wherever on the planet, right? Like it actually could be morning for some of you. I know right now it's 1 a.m. for Professor Wu, for example, not that he is paying attention to this, but who am I to judge where you're zooming in from? So it could be anything. Okay. We're going to get rolling again. I know it's been a long weekend. I stupidly have been trusting the notifications on my Google Classroom, like thinking that as long as I answer all the notifications, then I've graded everything. And I just learned the hard way this morning that isn't true, that there are certain things that come in without notifications. So I apologize. There's about 2 or 3 of you, maybe I'll even check in a second, about 2 or 3 of you actually, as of an hour ago, had done homework 4, and I did not turn it back yet because I honestly did not even think that it had come in, and I was wrong. So about 2 or 3 of you, maybe I'll even check in a second. I totally owe homework 4 to. Some of you did like game turns that I only just got back to because I didn't realize they were sitting there. I apologize, but it's awesome. Oh, someone else here. Sorry. Hold on. Okay, cool. No, and this is not my passive aggressive way of saying to anybody that you're late with anything. Really, I'm saying to people, like, I don't think you guys are late with stuff. In fact, I was about to and if you are about to submit, cool. Thank you, Shankia. And that counts as something. But I'm much more tattling on myself because I was sort of proud of myself for thinking that I was on top of everything. And it turned out I wasn't. So in fact, let me say right now, I'm going to say, at the risk of embarrassing anybody, and believe me, we are today, as soon as I start, for real, we're like deep in homework 2. And so if you have not done homework 4 yet, believe me, there's no criticism here at all. Like we haven't even gone over homework 3. It's not a criticism. It is the case that anybody who turned it in can certainly like screenshot and submit the fact, for the fact that they were super early or super on time or whatever, they can get those extra points. But no, nobody is behind. Let me just say very quickly, with homework 4, right, I graded 2. So there's, right, I'm just going to say, I don't want to embarrass anybody, but if you are Liani or Hoyin or Jacob or Caleb, I totally know that you turned in, or I have not gotten it back to you. I apologize, but I totally see that you did it, and that's awesome. And everybody else, no problem, truly. Okay, wait, and other people are coming. Sorry. But then other than homework 4, I think anything that anybody did turn in, any game, turn, or any homework, I think, unless it came in within the last hour, I think you got it back. Like, I guess that's another way of saying, if you turned anything in at all prior to the last hour and it wasn't homework 4 and you haven't gotten it back, maybe you should privately chat me or let me know or something, because maybe I am making a mistake somewhere. But everything else I think has come back. And the game turns, let me say quickly, honestly, oh wait, something in the chat. Sorry. Oh yes, you too. Thank you, private chat person. Good afternoon to you. And I did enjoy my week. How would we submit? Oh yeah. So right. Okay. Good question in the private chat. Now that we've assigned 4 homeworks, if you, and again, this is like a extra little bonus reward. It is not the converse of a punishment. If you happen to have turned in every, let me back up even further. We're definitely not getting to homework 4 today. And I'm not assigning anything new tonight. Like, you consider it a break night or a catch-up night or whatever. Like, I will reassign homework 4 to be due tomorrow. But before I actually change that in Google Classroom or anything, right, if you happen to be someone who literally did hand in homework 1, homework 2, homework 3, and homework 4 by the time that they were actually, technically assigned, if you have, I think you can screenshot that in your Google Class. Like, I think, it shows in your Google Classroom, like, because technically if it's late, it says done late, even though, again, I almost don't like that. And I don't want anybody to feel that criticism. But if you show your little profile or something, I don't know what it's called, but if you look at your own situation in Google Classroom and you've turned in the first 4 homework assignments, not late, just screenshot that and turn it in for the game assignment that says promptness or whatever, and you'll get like the bonus points for that. Just, and the truth is, and if there's any doubt in your mind, if you know you turned in those 4 super on time, but you're not even sure you can document it, you can write on a piece of paper, I think I turned all those in for, on my honor, I think I did turn them all in on time, like please check, and I can check for you. Like, it, and I do trust you guys. It's not about proving things, but it's just like, it just makes it easier if I don't have to. Also a question in the chat, homework 4. Yes. Quick. So I hope that answers that private chat question. A different private chat question about homework 4, which again, by the way, homework 4 is now on a totally different topic. Homework 3, some of you might still not have done, and I'm still not upset about that. We haven't gotten to homework 3, but to be fair, or to be honest, homework 3 is more practice on a more study look at what we've been doing in the class. So like, I think you are actually capable of doing homework 3 at this point, especially from lab people coming. Question, I mean, homework 4 goes in a totally different direction. It's like it looks out of nowhere. So it might look really scary, or it might look really surprising to some of you. So it's super okay if you haven't gotten to it yet, really. Like, I understand it is a different topic we have to deal with. But since I just got a question about it in the private chat, with homework 4, any of the questions that are asking you for numerical answers, which is the case for all of part 1 of homework 4, like all the beginning, where it's giving you numbers and it's asking you for numbers, then yes, using 6.67 times 10 to the negative 11th for capital G, for the universal gravitational constant, is the correct right thing to do. If you don't know what I'm talking about right now, don't worry about it, but I'll say it, but if in case you sort of do, let me say it again. Yes, wherever it's asking for numbers, saying that capital G equals 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Like, yeah, that's look upable on the web. It's the kind of number that we would totally give you on an exam. You don't have to memorize it at all, although you sort of accidentally end up memorizing it if you do enough physics. So yes, that's the right number to use, and that's the right number of significant digits to use for any question on homework 4 that asks for numbers. However, and at some point in homework 4, it devolves into just asking it evolves into asking general questions that where it just gives you letters. And once it's just giving you letters, I believe that happens. If at any point in homework 4, it's just giving you letters and just asking you for letters, then just leave capital G as the letter capital G. I mean, and that's just like a truism in life for physics, but we'll get to that. All right, let me, yes. Okay. Updates on the, so now I also see in the chat, good and bad news. Updates on the exam. So I'm being asked in the private chat, are there any updates on the exam, number 1? Is there a review, number 2? And how about the time frame we have for the exam, number 3? So I'll go, oh, someone's here. Sorry, hold on. So hard to, wait, someone, okay. As far as the exam, the one thing I will say is yes, I've decided I'm perfectly happy to give you the full weekend to do it, no problem. So it'll be posted. It will be posted. Realistically, I think it'll be posted Thursday night, not Wednesday night. If I post it earlier, that's just to your advantage. But it'll be posted Thursday night, and then you'll have all weekend to do it. If I can post it earlier, maybe I will, but assume now I'm going to post it Thursday night. And night, I mean like 5 p.m. Assume now I will post the exam Thursday, 5 p.m. And you'll have till the moment we walk into class Monday to do it. Like you'll have all weekend and all Monday morning to do it. And then it's due the moment we walk into class Monday. That much I can tell you. I have decided that yes, you can have all, because that's what people seem to want. I hate to ruin some people's weekend, but it does seem to be what people want. I don't want to spend all day talking about all today talking about it. Yes, there will be a review, meaning I will give you a practice document that gives you an indication of what the tests look like, and we'll talk about it to the extent we can. I will also give you solutions to it to the extent I can. I'm not going to do that right now. It'll all be a little rushed because this whole course is a little rushed, but you will already you will have a practice document and some solutions to it by like tomorrow and probably Wednesday. That's most of Wednesday. We'll end up talking about that. So what I will send you off. So Wednesday we will confront all nitty gritty questions and answers about expectations and about format and all that stuff. You'll have a document in front of you that I'll probably give you the day before, that even if you haven't worked on, then like I can walk you through. And that's why I'll then post the exam like a day later, so you can assimilate that. I will be able to be available by text and stuff to answer questions Wednesday to Thursday. I'm not going to talk I want to still progress through the material today. But yes, you will, by the time it's posted Thursday night, you'll already know what's going to be posted, and you will have already had a chance to, even though a rushed chance, because the whole course is rushed, but you will have had a chance to like practice and prepare for whatever's going to be on it way before it's posted. And yes, you'll have all weekend. One thing I have to say to be strict about, it will be due the moment we come into class Monday, which means you do have to come to class Monday and you do have to show up on, like, I will be strict about that. I have to say this again because I'm super unstrict about homeworks, and I know that can be confusing to people. I don't worry about deadlines with homeworks. I explicitly don't. But with an exam, the one thing is you do have to worry about the deadline, because then there's like a fairness issue and so forth. So you'll have all the way up till the moment we meet for class Monday, but then that's when the exam has to be in, and I will care. And that means you can't show up to class an hour and a half late on Monday with your exam. I mean, all your peers will know if you do, and they'll know what you've just done. And they'll feel like, well, why didn't we just do that if he can do that or she can do that? And I'll tell you right now too, I am not saying that I will not take an exam if it's late. I'm not saying that. Like, I will take it. I'm also not saying that there aren't extenuating circumstances. Extenuating circumstances happen, but what you all want to do is communicate with me in advance. Like, if things are happening in your life that will make the exam difficult to get in on time, I actually can be even more open to that than you might imagine, but you have to let me know while it's happening, like Thursday or Friday or Saturday, like give me a heads up, like, wait, I have to go to the hospital, da 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 da. I don't think I can get this exam to you on time. If you let me know, we'll work it out. But you don't, we will. But you don't want to surprise me on Monday or your classmates by just like lackadaisically waltzing into class, having taken the last hour and a half to work out solutions while everybody else, you know, managed to cut. I think you all understand what I'm saying. So what I'm saying is I am strict about when the exams due. I do make exceptions. I do, because I do think there are exceptions in life, but they have to be worked out with me in a human way in advance. Just like no surprises. Okay, that's that. And yes. Oh, to answer. Sorry. Okay, sorry. Yeah. Oh, okay. So I'm back to the chat. I hope that sort of answered the question, at least for the moment. Again, I know I'm just like layering my answers to this exam. I know an exam is stressful, and there's so much material we have to get through before I can. But yeah, I hope that's answering that. Now, looking back in the chat before we go back to the homework, thank you. That is totally a helpful suggestion that someone put in direct chat about that there's a way to get rid of their waiting room. I appreciate that. I'm actually aware of that. It is a little bit annoying for me to keep dealing with the waiting room, but actually it is, just for what it's worth, it is a conscious decision on my part. Like, I would actually rather have that annoyance and have a waiting room than not. And I know it's a little annoying to you guys every time you come in, but you know, that's part of the territory too. Like it does help me keep track of what's going on anyway, but I appreciate that about the waiting room. Okay, wait, I'm going to say something about that too, quickly. Again, I want to try to get some material, but there's like, I'm a spazzy guy. I think you all can see that. I do believe that a room of 28 people is really supposed to be a room of 28 individuals. Like, I believe that each one of you is supposed to individually get something out of this, which is why I actually like the whole chat thing and the direct chat thing. But yeah, as I'm sure some of you have noticed, often if one of you sends something in direct chat, sometimes I do stop right on a dime, like whatever I'm doing, sometimes, and I deal with the direct chat right away. Sometimes I don't. I know it can be jostling if I stop right away and I look like I'm being all disrupted, or it looks like I'm disrupting the class to deal with the private chat right away. But if I do that, first of all, hopefully I'm not saying the person's name. Hopefully I'm not embarrassing that person. That's definitely not my intention. If it looks like it's suddenly disrupting me, don't let that be a discouragement to you guys not to send me a private chat. Like, that's on me. I can choose to ignore it, right? Or I can choose to get back to it in 5 minutes. If I make a decision to stop the class on a dime to deal with the direct chat, it might not be a wise decision always. Sometimes it's a regrettable decision, but it is my decision. Like, you're not making me do that. You should use the private chat, and you should like come and go as you need to, if you all understand what I'm saying. Like, and I hopefully am not embarrassing any one of you when I do that. But you know, if I spaz out, that's me being spazzy. And it's also me kind of like, if I stop on a dime for one of you because of a direct chat question, because I've decided it's that important or blah, 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 I'm also just trying to send a message to the rest of you that the rest of you have that right as well, if that makes sense. So don't worry, like, I'm always spazzy that way. You know, it's me, not you, is what I'm trying to say. Okay, so on that, oh, is there a curve for my exams? Okay, here's a question in the private chat, totally fair question, and I totally understand why it's private, but hopefully, but it's worth repeating. Someone in the private chat is saying, is there a curve for my exams? Here's the fast answer to that. I mean, it's, the reality is sort of complicated, but the simple answer is, in general, you should assume that I'm not going to curve the exam. Sometimes I end up doing that, but generally speaking, you should go into the exam assuming that I'm not going to curve it. However, and then I'm going to give you a raw score that is your score on the exam. However, you should also assume 3 following, and there's reasons for that. But you should also assume, even though I don't generally directly curve the exams, number one, I often will give an extra credit thing right away. Like, if the scores are low enough on the exam or whatever, what I will often do is say something like, okay, if everybody does blah, or redoes question 1, or da-da-da, I will give everybody extra points on the exam. Like, I often do give points back on the exam very fast. I just don't technically curve. That's number one. Number two, one of the reasons I don't actually curve the exams is because this whole homework policy of giving the tons and tons of points for both regular homework and the game homework is that is how I curve all the grades at the end of the semester. Like what? Like your whole. Even though technically in the science department, at least last time I checked, technically we're not even allowed to curve. I think, but and the word curve can mean lots of different things. But I do curve all of the grades at the end of the semester. If by curve we mean adjust things so that adjust things so that, like, if everybody gets a 50, if everybody ends up with a 50 average in this class, it is not the case that everybody gets an F. And put another way, somebody always gets an A in this class. And when I say somebody, I mean more than one person. So, and that's even if all the exam grades have been terrible. So I do curve all the grades at the end. The way I do that is by adding all these homework points to your exam average. And the reason that it is a curve is I decide how much the homework points are worth. I decide on that scaling factor that I've mentioned to you guys before and is in the syllabus. And I'll just say this one more time, like, you're going to have this huge pile of homework points at the end, most of you, and it's going to be in the hundreds, right? Like, most of you are going to have maybe even in the thousands for some of you. Like, yeah, and in fact, it definitely will be in the thousands for a lot of you, right? Like, some of these homework assignments are worth like 250 points, et cetera, et cetera. So you're going to have over 1,000 points built up in a pile that are meant to be added to your exam average in order to make your final average. It's just, of course, I'm not going to add 1,000 points to your 87 average. What I'm going to do is divide the 1,000 by some number that will make it reasonable, like not cruel. Like, I will divide your 1,000 points by some number that will end up meaning that you'll get something like 9 extra points for all the homework that you did, 9 extra points on your exam average. So if your exam average was an 87, you would end up having a 96 in the class, which is an A. And the one, and I know I've said this before to some of you, but it is unusual, so I'm saying it again. The A, that's how your grades are protected against any particular like off day with exams. B, the reason technically that really is a curve, whether I'm allowed to do it or not, is because the dividing factor that I come up with, the way to divide all your homework points down, is a dividing factor that I come up with every semester looking at all the grades. I come up with a number that will make sure everybody's grades are good and reasonable. That number that I come up with every semester is the same for all students, of course. Maybe it's not, of course, but like whatever I come up with, believe me, it's the same dividing factor for all students, but it's designed to make sure that there are A's, basically. So in that sense, that's where the curve happens. I hope that sort of makes sense. But then because I have that whole system and because people, believe me, do get good grades in this class, I do think it's important for you to actually see and care about what you actually got on your exams. Some people are exam takers. Some people are not. I'm not even sure that I'm one. But exams are like a big part of life, and I want you, and on all the homeworks and all that, I'm grading like on effort and blah, blah, blah. But I want you to see the reality also of just like your performance on exams. And I want to leave that sort of pure. So generally I do. Last thing though. So in other words, the final answer is things are curved in this class. Believe me, they're heavily curved. They're just not curved at the exam level. They're curved after the fact. But all the other thing is, if I run into trouble, and this happened last semester, if we run into trouble on the first exam, either because you all have a really hard time with it, or because I have a hard time grading it fast enough or something, which happened last semester. If we run into trouble on the first exam, often what I will do is change to the weighting system so that I have in the past said things like, whichever of your 2 exams you do better on, I'll count more. Like, I can do things like that. I don't usually just drop one exam because there aren't that many exams, so it's like weird to do that. But I am often open to weighting your better exam more heavily than the other. But the bottom line to all this is, I promise, the one promise I can always make is whatever systems I do is to help the grades, not hurt them. I promise. I mean, and that's in the syllabus. And like, so I will never say something like, we're going to count the worst of your 2 exams as heavier or something. Like, no way. Like, that defeats my whole purpose. So I promise you that all the systems are there to help you. Okay. All right. Okay. Going back to the chat, so is there a curve for, and yes, to answer another question in the direct chat, yes, it is just a midterm and a final. We don't have time for anything else. As you can see, I mean, it's just a midterm and the final. But again, to remind you, how the exams work is the midterm counts, the final counts, and then your final average for Professor Wu, like your final lab average, in effect, ends up counting at, because that's like 33% of the course. What we do is we just take those three numbers together, your lab average, which constitutes a lot of work. I know that, like all your lab reports, all that stuff, but your lab average, your midterm score, and your final score, those three get averaged together as your exam average, those three numbers. And then we add all the homework points to that. And again, the average number of points that people get for all their homework, the average number is around 8 points. Like that's 8 grade point, 8 percentage points. Again, the typical average is, if you had an exam average of like 85, you would end up with a 93 in the course. Like that's very different, right? I mean, I don't know why I'm yelling, but it's not a true, which is why a lot of the grades, and I mean, a lot of people were panicked last semester. A lot of people are often panicked in 203. They're especially panicked if I don't get things back quickly, or I mean, as quickly as I should. But then I think a lot of people found in 203 last semester that their grades still worked out okay. Like that often is what happens. I don't mind if you're a little intense during the course, but the grades are not designed to hurt you. Is there an extra credit question? So I'm still in the chat here. Sorry. Oh yeah. No. Okay. I think these are the last two questions in the chat. I think, at least for now. First of all, and maybe I already answered this, someone in the chat did put like, will there be an extra credit question on the exam? Last semester, Professor Walters gave us one. It was very beneficial. Obviously, it can be harder. So yes, I mean, I may or may not put the extra credit right into the exam. It sort of depends every semester and what we're up to at that point. But there definitely will be extra credit opportunity associated with the exam, whether it happens after the fact or not. I mean, almost definitely. Like it may happen after the fact. You might get the extra credit thing after I see the grades and turn them back and say, okay, we all need this extra credit or something. But yeah, there probably will be extra credit one way or the other. And then the average for the exam last semester. So someone asked me, what was the average for the exam last semester? If this question means what was the average for the first exam in this course, I'm going to interpret. All right, wait. This is a fair question. The question here. The question here. Oh, okay. Cool. Okay. So let me be clear about this, because actually that's even a better question than I realized. So, right. The question says what? Yeah, no, it's not you. I love it. Totally not you. It's totally me, but thank you. And that counts as closing the blah, blah, blah. Right. So the question says, what was the average for the exam last semester? Meaning, like last time I taught this course, Physics 204, what was the average on the midterm exam? That's a really important question, because even after everything I just said, or especially after everything I just said, yes, it's actually important for me to warn you. The average was low. I mean, I'm glad I think I can look it up. Maybe I'll look it up in a minute, but it was the average for the midterm in Physics 204 last semester, and 204, because again, I had a problem grading the 203s, but the 204, everything was super efficient and super thorough for whatever reason. And yeah, that first exam, I just want to, and also we had 2 sections of 204, it was like very big, but I believe, to be honest, the averages were like 63 and 61, the raw score averages on that exam. I'm saying that to be honest and to answer this very fair question. And I'm not saying it to scare anybody. And what I am trying to do, but it sort of dovetails back with this whole business of, do I curve exams or not? And the answer is no, but I do curve the grades in the end. Like what's important to realize is, yeah, the exams are hard. And people often do badly on the first, or people often do get low scores on the first exam. Any one of you might well get a number on this first exam that makes you feel like you're failing the course. I'm here to tell you right now that you're not. And I could, from all of you, in fact, I was going to start with a more positive message. Like you guys are totally handing in all these game things. Like a lot I found this morning, I didn't even realize you had turned them in Like you clearly were having communication. The mere fact that you guys all understand the video game assignment, the closing the conversation assignment, the fact that a lot of you have already done homework 4, let alone tons of you have done homework 3. I think we are having good communication. I think you're knowing what's going on. I think you guys are like in this course. It is plausible that some of you will get things like in the 60s or lower on this first exam because exams are real here, and we will. And I'm not saying that to scare you, but I'm saying, and I do want you to take it seriously. Like I want you to study. I want you to put this material together, especially those of you who are just grasping the chain rule for the first time now. I'm going to say like, great. And I won't put I'll take that seriously. And maybe the exam will have to like heavily stay in chain rule land, but then let's learn the chain rule, if you know what I'm saying. Like I do want everybody to learn the stuff that we're trying to do here. If there's certain stuff that we never get to, because we're going deep in the stuff that we're doing, then so be it. And then those things won't be on the exam, and we'll talk about that. But yeah, like the exam can be hard, and even though it's take home and all of that. So the honest truth is, on the first exam last semester in Physics 204, I think the average in one section was like a 61, and I think it was like a 64 in the other section. I think I can verify that. But I also will tell you that most people in the course, they didn't get as many A's as in 203. There were more A's in 203, but there were a ton of A's and there were a ton of B's, and very few. I mean, there was like B minuses and stuff, but there were the people that got a D or an F in that course like never turned anything in. I mean, really, anybody who took the exams and did stuff, they were in the A's and B's for the most part. It worked, for the most part. So I do want you to take the exam seriously, but don't panic about it. But the homework is practice for the exam, not just in terms of the material. But if you think I'm being picky, or you're getting used to my style, if you don't like my style, but you're getting used to it, like you see what I'm looking for in the homework, and you see what kind of steps, and you see how I mark the homework, like that's what the exam feels like. I'm looking for step. Same deal. Okay. Okay. It is a little bit scary, and I don't mean to. It is a little bit scary, but but it does work out in the end. But the highest grade. Okay, there was not 100. I do remember, and sometimes there is. There was not 100 in Physics 204 last semester, but there was like a 90. There was at least 196 and a 94. I can look this up also and get back to you. But yeah, there were A's on it. And also remember, when I say the average is, it's also important to know what the standard deviation is if you took statistics, because like when I say the average is 61, this is what standard deviation means, right? If I say the average is 61, that could mean like everybody got a 61, or it could mean that there were a bunch of hundreds and a bunch of zeros, like the distribution, and that's what standard deviation measures. The truth of the matter, and the higher the standard deviation, the wider the distribution is, if that makes sense. So just to be honest as possible, without looking it up right now, when I say the average was a 61, there certainly were scores in the 90s, and there were scores like in the 20s or whatever, mostly for people that gave up in the middle or didn't try or handed it in super late, which is also brings us full circle. I'll take it if it's late. I'm not saying like if you're 2 minutes late, then the gates of hell crash behind you and like I never speak to you again and I burn your document. I'm not saying that, but I'm saying if it comes in late, there will be penalties, to put it mildly. Like I can't look at your exam the same way as I look at everybody else's if it comes in late. It's just not fair at that point. But okay, all right. I'm not saying any of this to scare anybody.
Professor.
Yes, sorry.
Email you. Right.
Wait, it's hard to hear you, Edie. Wait, say it again. I'm sorry. Say again.
Now I'm asking, you said that you don't, there's going to be penalties for late exams, but are you including those one that I already spoke to you about doing it at a later date?
Oh, very fair question. No, I'm not. No, wait, let me say that to everybody. No, very, very fair question. Let me be clear, but thank you for listening. Like when I say there's penalties for being late, I mean for surprise late, for a late. No, if someone talks to me, any of you, like even right now, or you text me or something, and it could even be like Saturday. If someone texts me and say, I'm suddenly in the hospital or blah, 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 or like I'm going through a divorce, like and by the way, and I don't need like records from the court, but just if one of you as a human being reaches out to me and says, awful things are happening right now, I can't deal or whatever, can I please like appeal to your humanity and have more time with this? No, we'll make an arrangement. And if we make an arrangement, I mean, if, you know, if I believe you and stuff, whatever, we'll make an arrangement. And then if we make an arrangement, there won't be a penalty. No. And I definitely won't trick you. I won't be like, yeah, that's fine. And then you hand it in a day later. And then I'm like, yeah, that was fine. And I'm taking off 25 points. No. No, if we make an arrangement, that means we'll make an arrangement where you're fine. Or at worst, let's say I think somehow what you're saying is kind of sketchy. Like you're like, oh, professor, you know, I ate too much chocolate. And like now I think I need 4 more days to do the exam because of the chocolate. Like, I might be like, all right, well, if that's really your view of the situation, if you can afford paying 5 points on this exam for those 4 days, I'll make that deal with you. Like I'll take off 5 points, you know, and if you're like, yes, it's worth losing 5 points to have 4 more days so I can eat chocolate, we might do something like that. But I will totally not surprise anybody with a penalty. If we make an arrangement, if you say, here's my situation, and I say, I totally understand, which I generally do as long as people communicate with me, then no, then there won't be a penalty. I mean, that's a very fair question. I hope it's clear what I'm saying. There's penalties if you just surprise me. If you just all of a sudden your exam just comes in late and there's not even, you know, I mean, this has happened before. I'm sort of shocked. Like sometimes people will just like hand it in a day later and not even say anything. Just like, here you go, prof. And I'm kind of like, really? I mean, really? I'm just supposed to take that? And all your colleagues are supposed to just take that? And then I do a penalty. But no, if you've talked to me, no, then we work it out. And there's no, you don't surprise me and I won't surprise you. I hope that makes sense. But that's a very fair question. Wait, did I answer the question? I mean, does that, or Edie, or does that answer the question?
Yes, Professor. Yes, Professor. Thank you.
Right, okay, thank you. All right, awesome. And that counts as points for you for closing the conversation. All right, awesome. Okay. 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 And people are joining again. All right, so we should get back to material now. Okay. Did I forget anything? Okay, that answers everything. Yeah, I think that answers. Okay, people are coming. All right, so let's switch back to the material. Oh, okay. Yeah. All right. Let's just get back to material now. All right. I mean, there's something I'm. Yeah. All right. We'll get back to material. Okay. So I'm going to switch the board. I hope you can see the board. Yes. Okay. So we're going to go back to material now, which means I'm going to go back to where we were in homework 2. I may start moving a little faster. I might not do every single exercise, but I'm going to do homework 2. My feeling is, people were really honest last time and sort of showing me in more ways than one where some of the calculus might not be so comfortable for them. And we went down a thing last time where I tried to straighten out some of the calculus for people. I want to say again, I think that was totally worth it. It seemed like people were getting something out of that. If we're getting calculus now, I don't care whether it's the first time or not. In fact, I'm sort of thrilled to be part of it. If it means we seem like we're slowing down to some people, I'm okay with that. I guess this is the thing I was about to say a second ago. If we never get to certain things in the course, I'm even okay with that. I mean, there are to a point. I mean, I do want to get to the ending especially for people who signed up to see certain material, and because certain material is lovely, but our goal is to get what we can get. And because even if I get to the other advanced material, if you never understand the fundamentals, then we're all just BSing ourselves anyway. So what am I trying to say is that, again, what's going to be on the exam is what we've done here, not anything that we haven't done. But let's therefore really try to do this right. So, okay. So, we're on homework 2. I have to now pull it up. I'm sorry. All that talking and I don't have it pulled up. 1 second. But I believe we're on question 2 of homework 2, I believe. Hold on, pulling it up. Okay, question, yes. Okay, and yes, everybody who's, so about 10 people out of 18. Oh, about 18 people out of 28 have turned it in. They all got it back. I think there's 10 more people that still want to turn it in, and they still should and could, and you can use what we're doing here as benefit. Okay, I think we did, here we go. All right, I think we did. And obviously stop me if you can't see the board or whatever. I think we did the first question. Okay, I think, stop me if I'm wrong, but I think what I just wrote is a summary of how far we got already last time. And hopefully you see, like, it started from a different angle. I mean, question 1A just started with this random function, and we just randomly took two derivatives. But what we were going like forwards there. Where we try to end up in is seeing, oh, when you take two derivatives, you get this differential equation. Oh, so that means that that function that we just differentiated is a solution to the differential equation. It's just trying to answer what we've been doing in the lecture or in the lab from the, it's almost like it's the verification, it's the check, it's the proof that x equals a cosine omega t is a good function to use to describe something going back and forth and back and forth. Because when you differentiate it twice, you in effect get Hooke's law. So it's sort of like B is like the reason, B is the reason that we're going to keep describing oscillators over and over again with this cosine function, because it works, because it satisfies Hooke's law. All right, for whatever it's, all right, so that's where we were. Now then, oh, sorry, yeah. Sorry.
We get Hooke's law essentially without the mass on the left side, is what you're saying, right?
Exactly. Exactly. Beautiful. Right. Okay. So then now what it's doing in C, and a lot of you who turned this in totally saw this. In C, it's like now cutting to the chase. It's like assuming that you now see how this works, assuming that you now see what the deal is with something being a solution or not to a differential equation. Can you just do the steps on your own now? Sorry, I'm teaching with it right now. Right after I'm teaching. But your iPad is inside. I'm teaching with my iPad. You can have it right after this is over. Because I showed you it's the whiteboard. I'm in the middle of class right now, but it's the whiteboard, remember, that they look at. But when I'm done, you can have it. Well, I'm trying, but I'm not good at cheating. I'm too honest. Okay, I will. Sorry. Okay. Love you. Okay. Yes. That's super private chat. Okay, wait. Right. So now we're going to do the same steps, but it's just up to us to do them. Right. So in C, it's giving us the function. And the question is, okay, and what the answer is going to be no. I'm going to show, and most of you, anybody who did this, I think, did do it right, which is great on the homework. The answer is going to be no, and maybe some of you can even just see that in your mind, but you don't have to see it in your mind. We're going to find out. And I could turn back the page if you want. Hold on, I'm losing it. The way to find out is to differentiate twice, to take the function and differentiate. So the function was this. I already forgot whether it was a 3 or a 5. Great. Okay, it's 5. So here's the function. So if now I'm going to do this a little bit faster than before because I think we are practicing it now. I'm going to differentiate it once. So it's a trigonometric derivative and its chain rule. To cut straight to the chase, I get this.
Can you go to the previous page, Professor?
Oh, yes, absolutely. Okay. Sorry.
Thank you, Professor. I'm done. You can move forward.
Cool. Thank you. No problem. And that counts as closing the conversation. Okay. Awesome. Right. Okay. So we have this function a cosine phi t, and I'll say also just part of what we're trying to practice here, everybody, is getting used to the distinction between variables and constants. I'm using a as a constant here before the cosine. In our other notes, like from other examples, and in the lab maybe we use x naught. I'm intentionally doing that because I want you guys to get that flexible and that versatile. Like sometimes you'll see it as a, sometimes as x naught. They do mean the same thing. They're two different ways. They emphasize two different things. Like a is used to stand for amplitude. X naught is there to stand for initial position. They ultimately are one and the same thing, but it's two different ways of thinking about the idea. Like x naught is the very first position that the mass ever has. A is the maximum position it ever has. So they are two different meanings, but it turns out that's always the same thing. The very first place the mass ever is, assuming it starts from rest, will be the maximum that it ever gets. So, okay, so A here, whether it's a number or whatever is wow. A here is the same thing as, oh wait, oh, 1 second. Oh, hold on. There's hold on 1 second. Wait. One second. Hang on 1 second. Sorry. Okay. All right. So sorry. Total interruption on my side. That has nothing to do with this class. Okay, so A and X naught are interchangeable. Okay, so I took the derivative. This is the first derivative of that, just like we did yesterday. Then I take the second derivative. And this is the second derivative. And this is practice now. Like this, I feel like we're practicing now exactly what we said in the last class, and it's more calculus than physics, but whatever. Just note, and I think most people who did the homework got this right, and you still can do the homework, blah, blah, blah. But do notice a subtlety. Like notice the 5 got squared and became 25. The A did not get squared, right? Like the A is a constant, it's just going along for the ride. But the 5 from chain rule came out twice because we took 2 derivatives. I'm not explaining that well, but just notice it's not a typo. The 5 came out twice. The A just sat there the whole time. So we get this. So then the question is, And the answer is no, because the answer is no. Because evidently, like when we take this function and we differentiate it twice, we get itself times 25 times a negative sign. Like that's what we just found. That we get back itself times 25 times the negative sign. That's what equals its second time derivative. But the question was, going back a page, the question was, do we get back itself times a 3? Like it's just that, I mean, it's just that dumb in a way. In other words, i.e. 25 does not equal 3. They're not the same thing. So this is just an example to say, it's not that all cosine functions satisfy all differential equations or something like that, or it's not that just any old cosine function satisfies Hooke's law. It's that the actual angular frequency has to be correct. What we're really saying here, okay, so the first question in the homework, the function was a solution to the differential equation. In this homework exercise, the function is not. And all of just because we put a 5 there instead of a 3, basically, or we really, because we put a 5 there instead of a square root of 3. Let me be explicit about that. Now, let me be explicit about this. This may be obvious to some of you, or it may seem like extra confusing detail to others. But what I'm saying is, this last example didn't work because we were being asked, does something satisfy the differential blah, 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 blah equal negative 3x? Like that's what we were asking. And we're saying no, because it didn't work out, because once we differentiated twice, we got something that didn't work out with that 3. We could have made it work out with that 3 if we had adjusted the omega accordingly, the number right before the t in the cosine thing. Like what I'm really trying to say, like if you follow what I just wrote right here, and this is a counterexample, I'm saying if it hadn't been 5, if it had been square root of 3, then it would have worked, right? So in other words, what I'm saying, and tell me if you want me to go back a page, but what I'm saying, like the general principle to take away from this, Ah.
Professor,
Yes.
angular frequency is how many times a specific angle is seen within a period of 2 pi, right?
Exactly. That's
Gotcha.
what, yes. So, okay. And that's really good. And this is, oh yeah. Okay. And I see it in the Shakia's thing in the chat now. Sorry, but yes, but good. Right. Right. And this is so important. I almost should do another page on, write this bigger on a different page, but yeah. So angular frequency is exactly what Caleb just said. And angular, and we're going to deal more and more with that. It is, in a way, I can't put it better than the way he just put it. Um, um, but angular frequency specifically is measured in radians per second. It specifically does have to do with the cosine graph, or how often the cosine wiggles back and forth in a period of 2 pi, which, so I'm totally agreeing with that, but that can lose a lot of people in the room, right? Like, I know that once we're talking about like the cosine function wiggling or periods of 2 pi or radians, like a lot of our brains can glaze over. Not everybody's, but a lot, but mine certainly used to. So let me back up and also say, just remember, and we'll say this over and over again, remember always that there's 2 pi radians in every circle. There's 2 pi radians in every circle, and circle is just a mathematically precise way of talking about cycles. So in English, whenever we're talking about angular frequency, what we're really just talking about is how frequently the thing cycles. Like, we're measuring it in radians rather, and we're going to see this in a second, but we're measuring it in radians rather than just in cycles or something. And we have to adjust by this factor of 2 pi, but that's just detail. The concept, when we talk, and all this is to agree with what Shakia just asked and what with what Caleb just said. Why do I keep doing that? Sorry. This is totally to agree with what Caleb just said, but just to expand on it, like, whenever you guys see omega, I mean, it looks like a W, it looks like a lowercase w, but it's the Greek letter omega. That technically does mean angular frequency, which is what Caleb is saying. I'm here to add, if your brain glazes over when you hear angular frequency, just focus on the word frequency. What it really means in English is just how often this thing is completing cycles. That is what it means, is how often it completes cycles, how rapidly it's cycling back and forth. And so what I'm trying to say just happens to be measured in like radians in this funky unit. So what I'm saying here, what I'm trying to say mathematically on this page right here is, if something is a harmonic oscillator, its angular frequency, its rate of oscillation will always be specifically the square root of whatever that constant was in the differential equation. Like, whatever, in other words, if it's literally a mass over a spring, it's going to be the square root of K over M. If it's something else, like just these mathematically abstract examples that we have here, where we don't even know if it's a mass on a spring, or maybe it's a pendulum, or who knows, if we know what the differential equation is, then, and the differential equation always says like d2x over dt squared equals negative some constant times the variable. Whatever that constant is, literally the square root of it will be the angular frequency. The square root of it will be the omega term in the cosine function, which is why we always call that constant omega squared. Like that is part of the intimidation of all this. It's part of where we lose people. I know that every time I write the differential equation, I'm writing negative omega squared z. So it looks like another square and it looks like, what? Wait, another thing is being squared. What's going on here? Is that thing a variable? Do I have to do something with it? No, we're just calling it omega squared. We could call it anything. We could just call it constant. We could call it J, but we're calling it omega squared because we're signaling ourselves, we're anticipating that the square root of it will necessarily be the omega in the cosine function. It will necessarily be the angular frequency. That's kind of like the big discovery that we're making here in a way. And we're just trying to see that from all these different exercises. But and that's why I changed my variable to z when I just wrote this page. I wrote z just to try to emphasize this is true no matter what we're talking about. And again, also, this is kind of like what either Caleb or maybe it was just someone before said, like, every time I call this Hooke's law, yeah, it's Hooke's law with just like dividing out the masses on purpose, because I'm saying it's the general truth that we get out of Hooke's law, even when we don't literally have masses or masses of that kind, even when we have a pendulum or something else. All right, I'm gonna go on, but yes, like totally good question, totally good answer, and thank you. Okay, all right, so I'm gonna go. All right, that's probably too much on that anyway. All right, so next question. So that was C. All right, now I don't know, it's kind of slows down again. Now go back to D is kind of the same thing. I'm just gonna hopefully do it a little bit quicker. D is, so we're still on homework 2 here for those people tuning in and out. Homework 2. Oh, yeah. Oh, and I see what's happening. In D, they're just sort of asking you to prove what you already figured out in C. It is kind of redundant, so I'm just going to write out the answers, but it is kind of redundant.
So, Professor, you're saying the angular frequency is represented in as it is over 1 second. Like if it completes 7 cycles in one regular period, we would just I can't, I'm not able to put it in perfect words, but we would just say how much it completes in 1 second. So if it completes 7 cycles in one period, then it completes and say one period takes 2 pi seconds, then it would complete 1/7 of 2 pi seconds in 1 second, right?
That is very good. Yes, that is spot on. So let me say that is spot on. And I want to explicitly say that to everybody in like a couple of minutes. I'm going to write that out. But yeah, and yes, you got it. And anybody who followed what he just said, you got it. And if you didn't follow what he just said, don't worry. I'm going to say it again soon. But yes. So yes, very good. And totally put that in one of the game sort of thing. But yes, you got it.
Yeah, it's hard for me to put the concept in like the decimal form in my head while I was listening. So
right, it is hard to articulate, and it's one of the reasons. And I've got a way to write it down for. No, right, but I totally know what you're saying, and it's right. And I'm going to put it my way in a couple of minutes when I have like room on the page. But yeah, you're all over it for real. That's awesome. It also makes me feel like something's happening in this class, which is good. So okay, and again, anybody who heard him but didn't catch what he's, don't worry, I will say it again a different way soon. But all right, so this is that. Right, so all right. So what I just did in, I'm gonna try not to overtalk this. What I just did in D is what we already kind of, it's just checking what we already must have done in C if we got C right. So it's actually, anybody can ask questions. I don't mean to blow it off, but I'm gonna move on. Right, sorry. But I'm just gonna move on. Yeah. To the next one, which is E. Okay. Oh, and E, yeah. E is more practice, but someone did ask me a good question about this last time. I think either Shankia or Juanita asked me something good about this last time. So quickly, No, it will actually, I know who it was. Sorry, I don't mean to mention names when it's not appropriate. And again, we're practicing, right? We're just trying to see how whether or not the math, when the math does look like the physics or it doesn't, it's still the same math is kind of what we're trying to say here. So now instead of calling that thing 5 or 3 or omega, we happen to call it square root of k over m. As far as the math is concerned, it's still just a constant. It's still treated the same way when we take derivatives. It's just physics-wise, we're kind of saying like, oh, what if we happen to know that we actually have a mass on a spring, where we happen to then we happen to have more knowledge about these constants. So we're just putting that physics detail in, but the math should work the same way. So actually, I'm going to go on the next page. Sorry, I can turn back if you want. Tell me when, but I'm going to go back to the. Oh, and I don't know why the Roman numerals did what they did. That's sort of not on purpose, but on the next page.
Also, you said that the units are in radians per second. Is that always the case, or is that specific to this scenario?
That's a great question. That it is always the case for omega. For the angular frequency, for the square root of the constant in the differential equation. Yeah, for all simple harmonic oscillation, whether it's mass on a spring or pendulum or electric field, yeah, it's always radians per second. That is a good, yeah, that's a good question. And I think that actually comes up in homework 3 as well. But yes, good question. Okay. All right, I'm just retyping this because I ran out of, I'm not saying anything new here. I just ran out of room. And I don't know why this is called Roman numeral 3, but it is. So dx dt, I'm going to do the same thing. Chain rule, so the constant comes out. And even though it's a complicated looking constant, it just is a constant. So I get this, but it stays. I mean, it comes out, but it also stays, if that makes any sense. And I keep being, I guess I'm being inconsistent with my parentheses. So the point is that whole square root of km thing comes out from chain rule. And then when you do the second derivative, it comes out again. And so the square root of k over m times the square root of k over m is just k over m. So I'm being sloppy here, but so we get that. And now that's the answer. And I should circle these answers. That's nothing. Please circle answers in homework. I mean, I guess even I'm getting sloppy about this, but please do circle your final answers in homework. And if I write PCA, it means please circle answers. This would be my answer, and I can move on, but and I would move on if I'm a student, or I just turn this in, I'm done with this, I move on to the next one. But just as the teacher for a moment, let me point out, like, notice. Notice, I could just, everything's multiplication, so I could move around the k over m and the a. And if I do that, notice then that this whole thing here is x, right? That whole thing is x. So even though no one asked me here in this question, just notice, if someone asked, is that the solution to the differential equation d2x dt squared equals negative k over mx? The answer would be yes. In other words, that is the answer. That would be, that cosine function is the answer to the Hooke's law differential equation. In other words, that's how we got our answer to question 9 of homework 1. We're just showing the same thing again. What the rest of the math exercises are trying to say, it doesn't necessarily have to be a metal spring with a K or a block of mass with an M. Like, all this math still works with anything that's oscillating. But here we're reminding ourselves, yeah, specifically, if it's a mass on a spring oscillating, this is where it came from in the first place. I don't know, for whatever it's worth. But okay, that's the answer to that one. I'm just going to keep going. You guys can stop me. I'm just going to keep going because I'm going to keep going. One, because I think we're clear unless you stop me, but also because this next one, now we're going to get into something with this next one with F. And if there's, let me look back at the chart. This next one that we're on now, something slightly interesting does happen here. And people did raise questions about this on the homework, and it is kind of a thing. Hold on. And I don't know why the Roman numerals are doing what they're doing. Okay, so here's the question. I'm just going back to the chat. Okay, there's nothing in the chat. Okay. Oh, sorry, that's 3.5. Okay. Still all the same deal. It's just a new cosine. It's now a more complicated looking cosine function. Still all the same rules. When we differentiate, we do trigonometric derivatives, we do chain rule. But let me remind you about chain rule. Let me remind you of this. In a way, whenever you're thinking about derivatives, I think it's often best. Remember that derivatives are slopes, and remember all these complicated functions. Remember to bring them back in your mind to the one function that most of us are pretty comfortable with, which is a straight line function. Like bring everything back to y equals mx plus b whenever you can, because that's the thing we all understand the best. So remember, or recall, okay, I'm saying, like I could ask you guys, but I think we said this. Remember, if you have y equals mx plus b, I mean, if you think about it graphically, if you have y equals mx plus b, right? It looks like that, like this. It has some slope of m and it has an intercept of b, like it's a straight line, y equals mx plus b. If someone asks what's the derivative of that, what they're asking is what's the slope. And if it's a straight line, then by definition, the slope never changes. So the slope is a constant. The derivative of it will be a constant. It will just be that slope, m. Put another way, there's more than one way to think about this, but if you do the power rule, like the derivative of just b just being a constant number, b does not have a slope. The slope is 0. So no matter how you think, if you just think about it graphically, the slope of a straight line, y equals mx plus b, if you think about it graphically, the derivative of it is just m. If you think about it non-graphically, if you think about it in terms of power rule, in terms of taking the derivative of each one of those terms by itself, the derivative of a constant is always 0. Why? Because a constant graph means just a horizontal line that's always at one constant value and never changes its value, therefore never has a slope at all, right? Like the slope of a constant function of say the function y equals 5, right? If you just picture y equals 5, that means no matter what x value you pick, y is always 5. So that function never changes, it never rises, no matter how much it runs, and it never dips down. So its slope is always 0. Its derivative, its rate of change is always 0. What I'm trying to say here in as many ways as I can, that if I just see some function, blah times the variable plus a constant, then the derivative of that whole function is just blah, is m. Therefore, why am I saying this? And I can go back on this page if you want in a second. I'm saying therefore, if the function is this, let's say c, okay, what I want you to see, again, part of what we're just trying to get comfortable with here is that even if I scramble up the letters or life scrambles up the letters, as long as you know what roles the different letters are playing, you don't want to let your head get scrambled just because the letters get scrambled. So if you believe something about y equals mx plus b, I'm here to tell you same logic should apply to z equals omega t plus 3.5. As long as you understand, if you are getting, and I'm not saying you would have understood this right on day one, but if you're getting more and more comfortable, I'm saying that the z is just like y, the omega is just like m, the t is just like x, the 3.5 is just like b. What do I mean by just like? I mean that the t is the independent variable, and the other thing is the dependent variable. And so if I have a function, and there's a reason I'm calling this thing z, you might even say, wait, where did z come from? Why didn't he call it x or something? No, not x, because x equals a cosine of all this, right? I'm just looking at that little part inside the parentheses, the little part, which is like a function within a function, right? I'm looking at that little part, and I'm saying, if I look at that little part, is if I really believe, if I really understand that the derivative of mx plus b is m, then the derivative of omega t plus 3.5 is just omega. That's what I'm trying to say. I'm saying if right, if you believe, like go back to this bit, right? If y equals mx plus b, if y equals mx plus b, then dy dx equals m. If the function y of x is a straight line, then the derivative of that function is just its constant slope. Same thing here. If I have a function omega t plus 3.5, then the derivative of it is just omega. Nothing happens to, like, technically it's omega plus 0, if you like, which is omega, right? So that is the function inside the cosine thing. And the chain rule says that to take the derivative of a big function, we take the derivative of the, excuse me, the chain rule says to take the derivative of a function within a function, we take the derivative of the outer and then we multiply by the inner. This is the inner now, right? Like this is just like what we were doing yesterday or last Wednesday, but there's like a 3.5 thrown into the mix. What I'm trying to tell everybody right here, I don't know why I sound upset. I'm not upset, I'm just excited. What I'm trying to tell everybody is what to do with the 3.5. And the answer is kind of ignore it. Well, the answer is this, so I'm saying finally, and again, I know half of you just did this and did it right and don't need all this talk, but hopefully it's illuminating things anyway. I'm saying then, oh wait, whoa, hello. And notice all this too, again, for any and all of you. And again, I'm sort of dragging this out. I'm just trying to explain it. Like, I know that these are just all the steps that make us understand it. And also, by the way, let me also say, for those of you who think that you just know this in one step in your mind, for those of you who think you just already know it, it's still a really, really good exercise to be able to take whatever's in your mind and be able to break it down into as small steps as possible. It doesn't make you stupider, it makes you smarter, for real. For two reasons. One, when you finally get to something that you can't just do in one step in your mind, it gives you the model of what to do. And I'm not joking about that. Number two, the truth of the matter is, even those of us who think that we could just do things in one snapshot in our mind, like a lot of times we think that, but we're actually kidding ourselves. What we've done is we've flipped through many, many shots in our mind super quickly. So we think we just knew it. We don't realize we've gone through a thought process just super rapidly because we're used to it. And the more you can know, like the more you can know what thought processes your mind is doing, even when it, or especially when it does it super rapidly, the smarter you make yourself, for real. Like it does not make you dumber to slow down the processes of your mind and look at them and see what they are on things that you think you know. It makes you that much better at doing the things that you don't know, that for real, to everybody. But so, for example, right here, I'm saying, here's how chain rule works. It might be the case that last Wednesday when I wrote chain rule, I might have put the Y's and the Z's and the X's in different places. I'm not contradicting myself now, and I'm not trying to confuse anybody. I'm saying it doesn't matter what place you put them in. It all depends on the context. We want to get that flexible, but I'm saying if this time, if Z is the inner function, and Y is the middle function, and X, if X is the inner function, and if Z is the middle function this time, I don't think I said it that way last time, but if Z is the middle function and Y is the outer, then this follows, like the whole derivative itself must be the outer derivative times the inner derivative. And when you write it out, this is the chain rule. When you write it out in this notation, it kind of does look like it kind of makes sense, right? Because it almost looks like it's obvious because, the DZs just cancel. And so, of course, right? So what am I getting at? Dragging all this out, I'm saying, therefore, and this is actually kind of an interesting one. I'm looking at the time. Okay, what I'm saying is therefore, and again, I can turn back the page if and when you tell me to, but just to wrap this up, I'm saying thus, if the given function that we got was this, I'm saying then that in effect, this whole thing here is acting like Z, like the inner function Z. Sorry. Oh, well, yeah. And so we're doing in terms of T's, not X's. So I'm saying here, I'm writing it one more. I didn't actually intend this, but again, it doesn't matter whether I do Y, X, Z, Y, Z, X, X, T, Z. Like it's a chain rule. It says as long as you got something built on something else, this is how you build, or something linked to something else, this is how you link. So I'm saying here in this example, we're looking for dx dt. It's going to be the derivative of the outer times the derivative of the inner. In other words, it's going to be like the derivative of the inner. All my discussion 5 minutes ago was just to try to prove or explain that the derivative of that inner parentheses is just omega. It doesn't, the 3.5 sits there. We don't get rid of it, but the derivative of it is 0. It doesn't get, it's not part of the derivative. So the derivative of this whole thing is what many of you might have expected without that whole explanation. The derivative of the whole thing is kind of like the derivatives we were doing 10 minutes ago. It's a negative sign times an omega of the inner function. I can't quite say it better than that. Oops, someone else is coming. So this is, so answer 1 is that. is a long way of saying take the omega out, don't take the 3.5 out. That's what I'm trying to justify. So that's your first derivative. And then when you take the derivative again, the same thing again is going to happen. The omega is going to be part of your derivative of the inner function, but the 3.5 is not. And the 3.5 is just an arbitrary example. I could have made it 4.7. I could have made it the letter B. It just is some random number that stands for a constant. Okay. But so this is the answer to that. Now, did I ask? And I'll pause for a second. Did I ask? Oh yeah. Okay. So that's the answer. So that's the answer to. That's the answer to F lowercase 4. So then G, this is the important thing now. G, the question is okay, this is important. We now, we've been saying over and over again that the solution to the harmonic oscillator, the solution to Hooke's law in general is A cosine omega t. Now we just introduced a more complicated function. We just tried out, we just put on the table, well, okay, what about A cosine omega t plus something? Like what if we stick something else more complicated into the cosine argument? Like, what does that do? Does that change anything? Well, it does change some things, like it makes our derivative expression longer and it makes our second derivative longer, but evidently it doesn't change the super important reality of solving the differential equation. That is I mean, the answer is yes. In other words, the answer to this question is going to be yes. Show you why. Notice that even though the derivative of it sort of now has the 3.5 still in the parentheses, notice that we're now carrying along this 3.5 inside the parentheses for the ride each time we take a derivative. But that's exactly all that we're doing. We're carrying it along for the ride in the parentheses, each time we take a derivative. And it was there in the parenthesis even before we took a derivative. So in other words, when we take two derivatives here, we're getting back the original function times a constant times a negative sign, which is the whole deal. That's been the whole requirement from the start. Do we have a function which, when we differentiate it twice, we get back itself times a constant times a negative? And apparently here we still do. In other words, we can make our function more complicated, and whether we want to or not, we apparently can make our function more complicated by one term and still preserve still obey this requirement that we're looking for of getting back itself after two derivatives. So the answer is yes. It's still the case that the second derivative of our function equals the negative times the constant times the function itself. And that's a shorthand way of saying we're still obeying Hooke's law. we still have a harmonic oscillator here. Okay, that's important. That's important.
Professor, which question is this again?
Sorry. Did you say go back, or did you say go back, or did you say some? Oh, wait, you totally get.
No, I said, which question is this?
Oh, sorry. Okay, this is question G. Well, you totally get veto points. That's awesome. But this is question G. G of Roman numeral 1. It's Roman numeral 1 G on homework 2. So it's does that make sense? So it's G. Is X a cosine omega t plus 3.5 a solution to blah blah blah? Is that answer?
Oh, we weren't on homework 3 earlier, were we?
This whole thing, no, this is all about homework 2 still. This is
Oh, okay, gotcha.
cool. Okay. It's very, very much like homework 3. I mean, that's true. But yeah, this is homework 2. This is G, if that's cool. Okay. And what I'm saying to everybody then, okay, this is just, we just tweaked. We're just practicing the same example over and over in a way, but each time we practice it, we're tweaking it a little bit to see kind of the quest here is we start with a mass on a spring and we're seeing if we can make it more and more and more general. Like, can we infer larger and larger truths about like all of nature from just this little stupid mass on the spring? And what we just did, and I'm talking to everybody here, all I did was add in a 3.5 into that parentheses. But that 3.5 is an arbitrary example. Could have been any number. What we're showing now is that even if you throw in another number into that cosine thing, it still works mathematically, which means that we have a more general physical piece of information at our hands now. Let me be more specific. What I'm saying, and this now does go back to something Caleb was saying before, and some other people. Let me tell you what I'm saying. So I'm going to dwell on this for a bit. What time is it? 2:50. Yeah. So I'll get to everybody. And whether you're going in and out, like we're on G of homework 2, and this G thing is just an exercise, but it's meant to illustrate a new concept. Hold on. Okay, this is now a leap I'm about to make. So, I mean, I hope anybody, if you were spacing it for 1,000 reasons, if everything was super clear up until this point or super something, tune in now, because I am about to say something that's, I think, maybe a little bit new, and it's going to look like a leap, maybe, for a moment. I'm saying this. We just proved that if you stuck a 3.5 into those parentheses, it doesn't change the fact of that cosine working. by working, I mean solving the differential equation. Okay, even though we stuck in a 3.5 there, it didn't change the fact that when we differentiated twice, we still got back the function itself. Now, what I'm here to say is there was nothing special about 3.5 when we did that. The way we treated the 3.5 had nothing to do with the fact that it was 3.5. It had everything and only to do with the fact that it was a constant number. It could have been any number. We would have said that the derivative of any constant number is 0. Like that's what I was, and again, if you were tuning out for fair reasons, because like it all seemed old news to you, again, what I'm saying is if you have a function omega t plus a constant, the derivative of that function is just omega, right? Like you don't, like the derivative of constant is 0. And that's why we treated the 3.5 the way we did, because it was just some constant number. So I'm going to say now, okay, then that means we could stick any constant number we want into those parentheses. Like any constant number we want, we could stick it to those parentheses with a plus or frankly a minus. I mean, but the constant number could be negative or positive, so whatever. We could add or subtract any constant number we want to the omega t in the parentheses of the cosine, and it will mean something for sure. It's got to mean something. I mean, it's a different function. I got to here and now analyze to you what it could possibly mean, but apparently it will still be a harmonic oscillator. Whatever that number means, it's not going to change the fact that it's still a solution to the differential equation, which means it still describes the harmonic oscillator. So the first thing I'm doing right now is saying from here on in, whatever that constant number is, we're going to give it a new symbol. I mean, this is why I'm like yelling to everybody to pay attention now. I'm introducing a new symbol now. I'm writing like a circle with a vertical line in it, and I circled it in red. That symbol here, I'm introducing it. It is technically the lowercase Greek letter phi. Some people pronounce it phi. No one actually knows how to pronounce it because Greek is not a spoken language anymore. I mean, honestly, you could call it phi, you can call it phi. So it's like pi, but it's ph. That's what, and it's like theta, but it's turned on its side. It's a circle with a vertical line going through it. It's a super important letter in physics. I'm introducing it now. The reason I'm yelling so much is this is one of those funny moments in the course where like I'm writing it out for the first time and it's going to appear in your notes right now for the first time. If people aren't paying attention, then all of a sudden later on they see phi like weaving its way through their notes and all of a sudden it's there. And it's really easy for people to be like, wait, where did this phi come in? Like all of a sudden there was phi. Like what the heck is phi? Like he lost me when he was talking about phi. So I'm telling you right now, don't let me lose you now. Phi is not just coming out of nowhere now. I'm bringing it into the discussion now explicitly on purpose. Like we never said it before. I didn't expect you to know anything about it before. I'm now saying we're going to use the lowercase Greek letter phi from now on to refer to any constant number at all measured in radians. It's going to have to be measured in radians because it's inside those parentheses. It's part of something that the cosine is doing. You can only take the cosine of an angle or of a section of a circle measured in radians. And I also know that some people are still uncomfortable with radians. We're going to get to that. But to whatever, yeah, totally. You're going to use it on the exam. Yeah, good question. Oh, yeah. Like, I think if you used it before now, that might be somewhat sketchier. You'd have to justify yourself or explain where you got it. But from here on in, absolutely, you can use this letter phi on homework or an exam. By the way, the two people that just asked me that in the private chat, awesome. That's awesome. Okay, first of all, that totally counts as bringing it full circle. Second of all, the two people that just asked me about this in the private chat, I totally appreciate because that shows that they're paying attention to what I'm saying. So I totally appreciate it. Yes. Okay, so what is it? Well, all right, so I'm going to go to the next. You can tell me if you want me to go to the last page, but I'm saying from here on in, phi is like the general concept for that 3.5. It's any number that can be stuck into the cosine. It has to be measured in radians. So it means something. I mean, it has to be measured in radians because you can't take the cosine of anything but radians. And this is going to force me to explain radians a little bit better to some of you who I think maybe would like a little bit more explanation of radians. But let me start by saying, Okay. First, so let me say what that thing is. Okay. So first of all, I'm saying that symbol, that upside, that like rotated theta thing is called phi. It's lowercase. We use it to stand for phase constant, not coincidence. Phi, phase constant. Okay. The phase constant is kind of like x naught in the expression back from physics 1, in the expression x equals 1 FAT squared plus v naught t plus x naught. It's like an initial position. That's what phase actually is like. It's like an initial position, like an initial head start that an oscillator has, or an initial like back position, like initial delay, depending on whether it's positive or negative. It's either how far ahead or how far back an oscillator starts in terms of its cycling. Okay, it's measured in radians because it indicates how far ahead or how far behind in cycling an oscillator is. So we're going to flip the page. So this is going to get us now into the thing that Caleb said like 20 minutes ago. This is going to get us into why with all this radian talk. Like, hopefully it's starting to get more clear in lab. And I do at some point soon want to check in with you guys about exactly what's going on in lab. But like, I think you're up to lab 4, but no, you must be past lab. Well, I'll find out. But actually, if anybody's listening to me right now and getting restless, if you want to just put in the chat or the private chat, just like the very last lab you did and or the last lab thing you had to hand in, I would be interested to know that. If you're, oh, thank you. Awesome. That was fast. You're so paying attention. Thank you. Lab 3. Okay. Oh, wow, you guys are really paying attention. Thank you. Wait. Also, lab 2. Okay, you're in the middle of lab 3. Okay, that's perfect. That's super helpful. And lab 3 is the shaking the long string thing, right? Like, I don't mean to get us digressed, but just so I know, because I do want to keep them paid. You're in the middle of the, like, well, I know it's a simulation. Everything's a simulation, but it's the long string. Yes. All right. Great. Thank you. And all of you that just responded to this, all of you that just said that, totally you should put in the, the game term thing. And maybe I got to think of a new portal to open up for like sidebar conversations like this, but totally thank you. Like Antonio, Catherine, Liani, Catherine, Tomika, thank you. Okay. So this, what I'm getting at now is going to help you, hopefully, ultimately with lab 3. It's like very related to lab 3 and lab 4, actually. Like I know all of a sudden we're talking in radians and omega is usually a big stumbling block for a lot of people. Like, they're sort of following what's going on and they can picture what's going on, but for a lot of people, like it all gets fuzzy with omega. And if you're still that person, the most important thing you can do to yourself is just admit, oh, I still don't get this omega business. As long as you recognize that you get other things, but you don't like omega, I'm here to clarify. We can clarify omega. And we usually do for anybody that recognizes that they don't get it. The real problem in physics, sidebar, the real problem that happens to all of us is like we're trucking along. Everything's always sort of straightforward to a point in physics, like maybe day 1, whatever. For most of us, what happens is we're trucking along. Then something like omega seeps its way in, or maybe in this case, something like phi seeps its way in. And the problem is, for most of us, if we start fuzzing out on omega, if omega is what's bothering us, it bothers us just enough to bother us, but we don't quite realize that it's omega that's bothering us, and we don't quite remember that we understood everything before. So the more omegas we see on a page, everything starts getting fuzzy, and omega starts infecting it all. For some of us, like not all of us, but definitely me. Like, if there's something that I don't understand, it starts infecting everything else. And then I start getting stressed out enough or fuzzed out enough that I can't even remember anymore what I knew and what I didn't know. And I'm just like, oh, this is a mess. I have no idea what he's talking about. I'm here to remind you again, if you're un-okay with omega, that is okay. Like, it's still very frequently the case that people are still not okay with omega right now. Just don't let it infect everything else for you. And if you're not okay with omega, you certainly wouldn't be okay with phi just now. But I'm going to take this opportunity to like move over. I'm not going back to homework yet. I'm now going to talk about omega for a little bit. So don't tune out because you don't like omega. Tune in because you don't like omega, if you see what I'm saying. And if, by the way, if you're totally cool with omega or you're totally Caleb or whatever, get a cup of coffee for a minute if you want. Maybe. But so this is going to be like I don't know if it's a sidebar, but like refresher on omega I'm going to give you right now, or deeper explanation of omega. Put it another way, what the heck radians have anything to do? Okay, the basic question that really does legitimately confuse a lot of people, even if they don't realize this is what's confusing them. The really, and it's a really important question. And whenever I say someone go get a cup of coffee, I'm kind of kidding because I kind of think like this could benefit everybody, even if they think they already get it. But I mean, obviously that's a judgment call. What I'm saying is we've been picturing a mass going back and forth on a horizontal axis. That was our original homework one, was something going back and forth. What we're trying, and we're analyzing the math like heavily of something just going back and forth, back and forth. The reason we're analyzing the math heavily is because we believe, I think I know at this point, that if I really understand the math of something going back and forth, then that math is going to apply to all kinds of systems going back and forth, even if they're not going back and forth in a straight line. Like the math of this will apply to a pendulum doing that, or as in lab 2, or as in homework 3, it'll apply to a temperature weather system oscillating in like heat values back and forth. It's ultimately going to apply to an electric field going more and more intense and less intense. Like ultimately anything that goes up and down, anything that cycles back and forth through dependent values can be mapped onto a simple mass on a simple horizontal axis. Like the mass on the spring is like our model for all of these oscillating systems throughout the world, including subatomic particles, including quantum mechanical functions. Like it's a big deal. We are analyzing the math of harmonic oscillation, and we're using as a model for it our simple mass on a simple horizontal spring. Okay. So and we're saying that all of these systems, whatever they are, can all be discussed in terms of like x equal or variable equals a cosine omega t plus constant. Like now, omega is supposed to represent radians per second, angular frequency. It's very easy to get lost and confused and think, wait a second, radians, whenever I did radians in math class or in trigonometry or whatever, radians were always like some angle thing that was like on the unit circle or something like that. Like radians have to do, and cosines go round and like curvy schmurvy up and down. So it's very easy to get lost in like, what the hell do all these curves and these circles and these angles have anything to do with going back and forth? Like even if we say that thing going back and forth has an angular frequency of 5 radians per second. Where are radians on that? Like I'm saying again, that's a legitimate confusion to have. And the most important thing that anybody could do is recognize that that confusion is existing in their brain. What's dangerous is that it might be existing in your brain. You might not even realize that that's what's confusing you. Now, what I'm here to say is the link between this and radians is that this is cyclical motion and radians are a section of a circle, and anything that's cyclical, we can analyze mathematically through the use of a circle. Circles are mathematically more easy to analyze. Like we know all the math of circles. Cycles are what we're here physically to analyze. So the connection, oh, I just lost, what did I lose? Oh, my board, hold on a second. I gotta put that back, sorry. But so the connection is radians. Let me just turn the board back on, so sorry, I don't know why, sorry. But in short, a rate, while the board's hooking up, what I'm here to say is radians are units by which we measure angles. Angles have to do with all of this because angles are not this. Okay, it's really easy to think that an angle is this. Like an angle is the intersection between two lines. I'm glad I'm not writing that down now because it's not right. I mean, it's not wrong, but it's like not helpful. Don't, from here on in your life, in math and in physics, don't think of an angle as an intersection between two lines, even though sometimes it is and all that. What it is, actually, what an angle is a section of a circle, a fraction of a circle, a portion of a circle. That's what an angle is. What do I mean by that? And I'm waiting, I'm babbling because, I'm not babbling, but I mean, I'm talking freely because I'm waiting for my board to rehook up to the intrawebs. What's going on here, folks? Hold on. Is this because I've run out of space? Come on. Sorry. Oh, I see. Oh, come on. Okay. Sorry. Just when I'm getting all worked up. What an anticlimax. Okay. The takeaway for the moment, while the board does, here comes the, yes. Takeaway for the moment is an angle is a section of a circle. That's what it is. That's what you want to think of for the rest of your life now, even if you never thought of it that way before.
In other words, it's a portion of a cycle.
Totally yes. And to be super specific, yes. Like, oh yes, yeah. And the key is that a full circle is, you could say in life, 360 degrees, right? But we're going to say here in math and physics, 2 pi radians. So our whole conversion factor, I'm going to write this down for everybody now that I got the board back, but yes. And from here on in, if there's any conversion factor that's actually important to memorize for this class or important to like navigate through everything, it's that one cycle equals 2 pi radians. With that, all this comes together. Well, okay, so but yes, the answer is yes. So okay, and this is another one of those things, like all of this was a fuzzball to me, honestly. Radians and all that stuff meant nothing to me until this following thing clicked in. And then like everything else, once it clicks in, it's like so simple that you almost want to say like, why didn't I get this before? But don't do that. I mean, any of you, there's no shame in not getting it before, but it is gettable. This is what I mean. Everybody knows what a right angle is. Like everybody in this, I know anybody who's paying attention right now, or even better, everybody knows what a 90-degree angle is. Everybody thinks they understand degrees. Everybody thinks they understand degrees, and they think they don't like radians for the simple reason that you learn radians way later in life. And honestly, that is the only reason. Everybody's habituated to degrees. It's a habit, and you see it all the time. Like snowboarders or skateboarders or whatever, like do a 360. So like my 6.5-year-old son who interrupted before and wanted my iPad and like plays video games all the time, like he totally knows what a 360 is because he hears about it all the time. He doesn't sit and question like, oh, I guess there's 360 degrees to a circle. So I guess, but if I asked him to divide that by 4, he'd be, I mean, or if I said, what's a 90-degree angle? He would know, right? And you guys would know, you know what a 360 is, you know what a 90-degree angle is, and you think you know, and you do know. And we think we understand because we've been getting that from such an early age, right? But it's not an understanding. We've just accepted the idea of taking a circle and dividing it into 360 parts, 360 parts. When we see a 90-degree angle, everybody can recognize it. Everybody knows the right angle is like this thing, right? And they call it a right angle or they call it 90 degrees. But what is it that they're recognizing when they see this? When you see that those angles there are 90 degrees, you're recognizing it and you've been trained to call it 90 degrees. But what you're recognizing is that that's a fourth of a circle, right? Let me make that clear. Like just like a 360 is a full circle, and my 6-year-old son knows that, and you know that. But think about it, even in terms of circles is kind of what I'm trying to argue right now. Like the 360, you know, is a full circle. The 180, you know, is a half circle. And you know, when you see a right angle or when you see a 90-degree angle, a 90-degree angle, or better, a right angle is half, excuse me, no, it's not. It's a quarter of a circle. You just know that. And to say that it's a quarter of a circle is a deep thing because it means you know that no matter how big the circle is, right? Like I could go like this, or I could go like this, or I could go like this. That angle there is a fourth of that circle, no matter how big no matter how big the circle is, right? In other words, an angle, and you can keep going from there. A 45-degree angle, you might not think it through consciously like this, but when you see a 45-degree angle and you think of it as half of a 90-degree angle, what you're really thinking is it's an eighth of a circle. That's what it is. It's not a distance between two lines, because if you want to measure a distance between two lines, that would be a distance, like measured in meters or whatever. And if you wanted to measure a distance between two lines, if you want to say like, well, this is a small angle and that's a big angle. If you think about it, if you wanted any consistent way of measuring, if you want to be like, this is a small angle because these two lines are closer, and this is a big angle because these two lines are farther, you'd have to agree in advance, where are you measuring between those two lines, right? Because, you know, if you measure way out here, they're very far. And if you measure here, they're very close. So, question? So, put another way, an angle is, sure, it's the arc length, the distance between these two lines, if you like, as long as we all have an agreement on how far in or out we're measuring. In other words, so what I'm saying is, well, so in other words, an angle theta is just an arc length divided by radius, which you've heard millions of times in math, right? You might have memorized it. I'm here to say, don't just memorize it or accept it as like a fragmented piece of knowledge. It's really the definition of an angle. That's why I'm drawing with, the triple equal sign as clearly as I can. I'm saying angle is just how far along a circle you're going, right? It's just how far along the circle you're going, but then divided by the radius, because that's just a way of saying, look, it's how far around the circle we're going. But if I pick a circle that's twice as big as yours, and then I would get an arc length that's twice as big as yours for the same angle. I don't want to get confused and think my angle is bigger just because I walked along more of the circle, if it's because I walked along a bigger circle. So what we're kind of saying is angle is arc length. Sorry. Angle is circular arc length per per radial length. Like angle is just arc length. It's just like how far along the circle you went. If you went all the way around the circle, that's a big angle. If you went halfway around the circle, that's a small angle. And literally, we could actually just use angle and arc length as interchangeable, except we want to take into account the fact that it shouldn't matter how big of a circle you went in. So if my circle is twice as big as yours, if my radius in my circle is twice as big as yours, we're saying take my arc length and divide it by 2, just so we're sort of saying like how much arc length did I travel per each unit of radius. It's just a way of normalizing the comparison. That's a proper math term. Or making the comparison fair so that all of our different arc lengths we're comparing are in effect cut from the same circle, right? So if you say that if you say angle is arc length per radius, it's S divided by R. You are really just kind of saying how much arc did you get per each unit of circle size that you have. So what we're really saying is take those meters of arc length, divide by those meters of radius, and the meters will cancel out, right? Like the meters will cancel out and you'll get a pure ratio, a dimensionless ratio on the right side. If you ever take the arc length of a circle and you divide out the radius, you'll get a pure a unitless, dimensionless ratio on the right-hand side. That ratio, ratios are fractions, that fraction is just expressing what fraction of a circle you traveled. So if you do this in degrees, you all of a sudden introduce this 360 business, but we're all used to it. So I'll say it for a second, like 360 degrees means go around the whole thing, right? 180 degrees means go around half the thing, half the circle. 90 degrees means go a fourth of that. But if we just do it purely with just this definition, if we're willing to drop that 360 habit, then we can actually get numbers that make more sense. We're just not as used to them, meaning this. If we were to apply this definition, and again, I think I'm saying things that most of you have heard before, I'm just trying to put it in a slightly different light right now. If you were to apply this definition, I'm saying an angle is just arc length per radius. That just is a way of saying an angle is a fraction of a circle. But now I'm saying if you want to do it in its purest form, take, for example, going around a whole circle. The arc length around a whole circle, would be the perimeter of that whole circle, or in other words, the circumference of that whole circle. The circumference of a circle, I should stop and ask you, but I'm not going to out of interest of time. So I'm going to write sidebar here. Like if you have a circle of radius r, if you have a circle of radius r, then the circumference, right, the arc length around the whole thing, the circumference, I know you know this, I'm just going to say, unless someone quickly wants to put in the chat, and yay if you do, but I'm just going to keep rolling it on. The circumference around a whole circle whose radius is r is 2 pi r, right? That's the circumference of a circle of radius r is 2 pi r. So according to this definition, I would go around the whole circle 2 pi r and divide by the radius r. In other words, if the radius was 1, then literally, if I have a circle of radius 1, then my arc length around the whole thing is literally 2 pi, like times 1. And then I would divide by 1. If I'm a bigger circle, I would go 2 pi times 2. but then I would divide by 2 because the rule says always divide out by the radius so that we're normalizing, so that it's a fair comparison, so that we're, we're just looking at how much arc length we go around per unit of a certain circle size. So if I go around the whole circle, it's 2 pi r divided by r, the angle around a whole circle what I'm trying to say here is radian is just the word for this concept. Radian is not even, it sounds like a unit. And yes, it's a unit that measures the same thing as degrees. But if you really look at it this way, technically speaking, neither degrees nor radians are actually true units. They're actually dimensionless. Radian is just a word, as is degree. They're both just words that are placeholders to signal us what's going on. Radian just means a section of a circle, and a section of a circle is unitless. Whether you divide the circle into 360 parts or you divide it into approximately 6.28 parts, each part is just that, a part of a circle. What I'm trying to say to everybody from now on is, if nothing else, you want to memorize anything, whatever you ever used to think of 360 degrees, think of it as 2 pi radians now. Please also know that if you were able to get used to 360 degrees, you should ultimately be able to get used to 2 pi radians, because 360 doesn't actually make any sense at all. You're just used to it. Like literally, if you want to know, like, why did anybody ever decide to divide a circle into 360 parts? There is a reason. I mean, there is a reason we decide to divide circles into 360 parts. And if anybody wants to rush into the chat, they totally can try to guess this. But it's, and when you hear it, it's super interesting, but it's also super has nothing to do with why you would have ever, like, it's super interesting, but it's not helpful at all. Yes, that is awesome. Yes. Yeah. So especially since you guys are paying attention, and since Caleb just said that, I'm going to dwell on it for a moment. It's particularly awesome because it's so crit. Well, yes, and that's also true. It is approximate. But let me back up for a second and say it's 100% the case. Like the fact that the Earth does approximately 360 of these for every one time that it does one of these, or actually even better, the fact that, because way back when this was invented, we didn't even think of it that way. Like the fact that there's approximately 360 sunrise sunset cycles for every one cycle of the sun throughout the entire astronomical sidereal sky. Like, because we used to think of it as the sun going around us. Now we think of it as us going around the sun. Either one is actually fine, believe it or not. But however you think about it, the fact that there's 360 rotational cycle, approximately 360 day-night cycles for every one cycle of the seasons, that great circle in the sky, which is where most original physics and original trigonometry and original geometry come from, the shapes in the sky. And no joke about this, like astronomy is the birthplace of physics, without a doubt. We can get all into that if we want, but we won't right now. But where we first started understanding the geometry of circles and the patterns of projectiles and trajectories and all that stuff, it all originally comes from us looking up in the skies. And the fact that there's approximately 360, and he's totally right, that is approximate, that's okay. The fact that it's approximately 360 day-night cycles for every one cycle of 4 seasons is means that that big circle in the sky that the sun makes around us can be divided into 360 little parts, 365 little parts. That is honestly, historically, and undoubtedly, I mean, incontrovertibly, why it started becoming convenient to divide circles into 360 parts, because originally we were doing all this geometry to apply it to the heavens. Now that is fascinating. And honestly, I've written books on that. Like, I'm totally into that. And I'm totally into the fact that Caleb said that, but I'm also into the fact that that's ridiculous. Like, none of you is thinking that, not even me, none of us is thinking about the solar system when we watch some skateboarder go like this, or snowboarder or whatever, or ice skater. Like, that's just history, that we took those circles in the sky and divided them up into 360 parts. And then we superimpose that understanding or that habit on circles on Earth and say, okay, let's divide circles on Earth into 360 parts. And then we teach our 6-year-olds this, and they of course absorb it, just like you guys did when you were 6, like, no problem, a 360. But that's all we did, was absorb a habit. I'm here to say now, if you can divide a circle into 360 parts, you can just as easily get used to the idea of dividing a circle into 6.28 parts, approximately. It was always approximate in the first place. It's still going to be approximate. You can divide a circle into 6.28 parts. Why do I say 6.28? Because that is 2 pi, approximately, right? I'm here to say now, but I really am going to approximate. I'm here to say now, and it really is a breakthrough. It'll help a lot. I mean, it helps me a lot anyway. I'm here to say now that for every circle, therefore every cycle, first thing I want to say, oh wait, something in the chat, sorry. And I am now approximating on purpose. And I'm really approximating. But if we want to, but the rest is just details. If you want to understand the concept, first approximate, and then you can add the details later. But we approximate all the time. We have to approximate somewhere. I'm going to look in the chat in 1 second. Let me say though, if people are still hanging on, pi is approximately 3.14, right? Like, it's not actually 3.14. It's approximately 3.14. It's 3.14 when we decide to go to 3 significant digits, because sometimes that's convenient. Oh, let me go a step further. It's not just convenient to go to 3 significant digits. It's absolutely appropriate and necessary if our measuring equipment only goes to 3 significant digits, right? This is where we are scientists, not mathematicians. If our measuring equipment only goes to 3 significant digits of precision, then it's actually improper and false, and like, it's lying on our part if we ever write down numbers that go beyond that number of significant digits, because we're then just talking about numbers that we made up in our head that we didn't measure, and then we're not being scientific, right? So we always in science are always approximating. There's always uncertainty. It's always limited by the precision of our measuring instrument. And by definition, no measuring instrument is ever infinitely precise, because you can't put infinite number of marks. Like, if you put in, like, if you think of a ruler, right, you're only as precise as the amount of space, you're only as precise as the number of markings you have on a ruler. The more markings you have, the more precise you are, for sure. The closer the markings are on a ruler, the more precise you are. But there is a limit, right? You can't put an infinite number of markings on a ruler, not just because you don't have time, but because if you put an infinite number of markings on a ruler, then they'd be infinitely close. It would just be one big black mark. That's no longer markings. That's just a piece of wood, right? Like, so literally by definition of measuring, if to measure means to see where something falls between markings, you need there to be a between markings. And as long as there is a between markings, as long as the markings are not infinitely crowded and bleeding into one another, which wouldn't be measurement, as long as there is measurement, there is a cutoff in how many significant digits we report. I mean, that right? So if you're okay with approximating pi as 3.14 or approximating 2 pi as 6.28, then I'm here to tell you, imagine sometimes we have a ruler that only has one marking on it or one significant digit, which in fact is the case when we're first looking at this material. If you're comfortable calling 2 pi 6.28, then for a while with me in your head, call it 6, because this whole concept will be so much clearer and it won't be more of a lie. It will be actually less of a lie. So what I'm saying, and I will look at the chat, I totally see those things in the chat. I'm sorry, this is where I'm spazzing in the other direction. I'm saying from now on, I think a cycle is 2 pi radians, or I think 2 pi radians is a cycle. Therefore, what I really think is a cycle is about 6.28, or in other words, about 6 radians. So what is a radian to me from now on? Like a radian is not 180 degrees divided by pi. Like, don't think of a radian as this complicated thing that's converted from degrees and then back and forth again with the unit circle. A radian is just, oh God, I just lost the Zoom connection. Oh no, I didn't. Okay. A radian is a 1/6 of a cycle, like literally, not exactly, but literally. A radian is just a 1/6 of a cycle. If you want to think of that as 60 degrees in your mind, you can. A radian is basically almost 60 degrees. Technically, it's 57, whatever. A radian is a 1/6 of a cycle. If someone said, and I'm going to get to the chat, I'm just like trying to spit this out, because this will now, we can use this gets us into homework 3 as well, and into the labs and stuff. From now on, when you see omega, when you see angular frequency, yes, part of your brain can think in terms of cosines and all of that, but you don't have to. First and foremost, first and foremost, and I will get to the chat, I promise. So if omega is measuring in radians per second, really what I'm saying is it's really just measuring what omega is measuring is how rapidly any oscillator is oscillating in cycle sixths per second. It's just radians are in effect cycles per second. Excuse me. Omega, angular frequency, in effect is cycles per second. And again, this is the thing that Caleb was saying like an hour ago. I mean, I'm not trying to like single anybody out, but I'm partly just trying to affirm that he was right and whatever he thought, like he does. And second of all, like just to also say that he wasn't off on some, like he isn't like a weirdo who was in some other land that you weren't in. I'm now just putting it in my words. I'm saying that omega measures how rapidly something is oscillating in cycles per second, but just divided out by a conversion factor of 6. If omega is measuring in cycle sixths per second rather than full cycles per second, simply because circles are mathematically more easy to analyze than just random cycles like that we don't know what they are. So again, I will get to the chat, but I just want to actually
I have a quick question.
Okay. Yeah.
You said a radian is 1/6 of a cycle?
Right.
Exactly, or is it?
No,
doesn't the pi throw it off a little bit, right?
Right. No, it's
okay.
not.
I didn't hear that. I got you.
Okay, but yeah, you're okay. Right. And to everybody, no, and this is important. This is the fine line between science and math. And believe me, I love both. Everybody. Sometimes there's times to be super exact, and sometimes I use triple equal signs. And sometimes, especially when we're trying to get our heads around something, sometimes it's really appropriate and helpful not to be super exact. Because if we jump, and I'm not saying this to Caleb, I'm saying it to everybody, like, right now I'm being approximate. I'm saying approximately a radian is a 1/6 of a cycle. It's actually more, which is like 60 degrees if you want to think of it that way. It's actually a little bit less. It's actually more like 57. But the point, what I'm really saying to everybody to say a sixth is just a fast way of saying like it's a small portion of a cycle. It's a portion of a cycle. It's like so small that it's like less than half, less than a quarter, but it's, you know, but it's bigger than a 20th. It's like a reasonable chunk of a cycle. So let me be more exact now to everybody. Let me, and I again, I know I'm skipping the chat from going. I just want to spit. Actually, no, let me look at the chat. Let me look at the chat. Oh, maybe. Oh, I did. All right. That was the Caleb thing. Yeah. Right. Days in the year, only approximate. Right. Okay. So that was the chat. So look at this now to everybody. We're gonna go two more step. Wait, 3, 4. Oh, perfect. Okay. So, and this is all, we can call this all sidebar 3. If I ever refer to any of this again, I'm going to refer to it as sidebar 3. I don't mean that it's a digression. Like this is not off the topic. This is not an accidental wandering. Like this totally is the topic. It's why that question in the homework was asked. You know, this is like how we do this course. So I'm always using the homework as like the pivot points for making these points. So we will get back to that homework tomorrow. I promise. We're not losing the homework. We're not forgetting about it. But we're just using each exercise to try to push our agenda forward. What I'm saying, so all this you can call sidebar 3 if you want, but it's very, very much germane to the material, like you would be tested on it or whatever. And hopefully this is helping lab too, what I'm saying right now. So I guess this is also a way of saying I'm about to give you 2 more equations, all of you, all y'all. I'm about to give you 2 more equations. If maybe you saw them in lab, maybe not, but they definitely are real equations from here on in. I think they just make sense. I think they're just definitions. I think you can understand them without rawly memorizing them, but one way or another, they are real knowledge. And so here's what I say, 2 more equations. One of them is this one right here. I'm saying, if you understand that, if we establish that omega is angular frequency, which is number of radians per second, which is again, like a number of people, including Caleb, said like hours ago, if omega is like how many humps there are to a cosine graph per every 2 pi period, which by the way is correct, but like I know to most of us, even me, like I hear that and I'm like, well, how is that helpful? Like, what is that? What I'm saying now is if omega is radians per second, if it's the number of angles carved out per unit time, what that really means is the number of cycle sixths per second. What does that really mean? It means if you really want to talk English, if you really want to think of things in terms of like normal everyday physical descriptions that make sense to most human beings, what most people would want to talk about is they want to get rid of all this nonsense and just say, all right, like, dude, like how many cycles per second is the thing making? Like if we're talking about a mass on a spring, like I just want to know, like how many times back and forth does it go, right? What I'm saying is, well, if we know the omega from the cosine stuff, if we did our math and the math popped out an omega, here's how to convert that omega to something physical. The physical thing would be standard frequency, just literally number of cycles per second. How many times there and back does something go? Like if it's a mass on a spring, how many round trips does it make per second? Or if it's a pendulum, how many round trip cycles does it make per second? I'm here to say it is, that answer would be whatever omega is divided by 2 pi. Literally, that's simple. Omega is in radians per second. there's 2 pi radians per cycle. So radians per second divided by radians per cycle gives you cycles per second. To put more concretely, if omega were if omega were 4 pi radians per second, if the math popped out that omega was 4 pi, like 4 pi, we'd all be like, okay, 4 pi radians per second, that's some cosine thing. Okay, 4 pi. What I'm saying is if omega is 4 pi, just divide that by 2 pi in your head or on paper. Know there's 2 pi radians per every cycle. And what we'd be saying is if omega is 4 pi, then f, lowercase f, standard frequency would be 2. If it's 4 pi radians per second, what that means in English is just 2 cycles per second. And that's exact, by the way. That is exact. I'm saying divide your number by 2 pi if you want it exact, and you'll get the number of cycles per second. I'm going to go, we have 6 minutes. I'm going to go one step further. I hope I'm not losing it. Also, my battery might be about to run out. But if you want to be approximate, just divide by 6. But if you want to be exact, you divide by 2 pi. So either way, when you divide by 2 pi, what you're getting is the cycles per second. Now we can go one step further, and this is where we're going to end today, obviously. But to summarize so far on this page, what we have so far. Wait, sorry. Whoa, okay. Sorry. This is the last page, I promise. Whoa. You know, a sigh is just a slowed down hyperventilation. Okay. I don't know what that means either, but okay. If right now
someone has their mic on, right?
Yeah, I think so. Yeah.
Just in case you didn't know, you have your mic on. Whoever that was, it just sighed.
Right, and now we've really.
No, I wasn't signed for the call. I was doing something, and it was just like it was. It didn't have anything to do with this.
You know.
All right, and I'm not trying to call everybody out, although I totally appreciate the video, but now I feel like I'm all right. Yes, everybody loves everybody. All right, what I'm saying now, and this is the last page either way. No matter what, this is the last page. I'm saying that f is by definition is whatever omega is by 2 pi. And what I'm trying to do with that equation, and you can memorize it, but hopefully you understand it. What I'm really just trying to do is get us from something super mathematical to something slightly more physical. Because the math, the cosines, and the differential equation, all that will pop out this omega. And don't forget, by the way, omega is the square root of whatever is the constant in that differential equation. Everything I'm saying right now is totally the key to doing homework 3. Like homework 3 is a snap if and only if you actually follow everything I'm saying right here. But if omega is the square root of that constant, or if omega is that thing in the cosine function, then omega divided by 2 pi gives you f. And f, what I'm saying right now, is measured in cycles per second. And I'm saying that's a much easier thing for all of us to relate to. All of us who do physics and who don't. Like we'd all rather measure in cycles per second than radians. We can picture the cycles. We can't picture the radians, any of us. Some of us just get used to the fact that what a radian is about 1/6 of a cycle. I'm going to go one step further though on this page. One cycle per second is such a common, such an important way of measuring the rate of any oscillator. Like oscillators definitely, by definition, always cycle. Who knows how fast or slow they're going? They're changing their speeds every moment, but they all cycle. So we all measure them all in cycles per second. So a cycle per second is such a standard, important way to measure things that it has a name that all of you know, whether you know it or not. 1 cycle per second is what's called 1 hertz. That's what a hertz is. Put another way, for example, 1 million cycles per second is known as a megahertz, as in radio stations. Okay, you don't have to know anything about radio stations for the moment, but what I am saying is from here on in, if you ever hear about anything in hertz, it just means cycle per second, which just means radians per second multiplied by 6 or divided by 6. We have, we still have 8. Wait, this goes till 3. Oh, we have 8 minutes. Okay, I'm rushing. It might be one more page. I apologize. It's just going to be a race between the clock, my concept, and the battery of my computer. But so far I'm saying to convert from angular frequency to frequency, we divide out the 2 pi, and what we end up getting are cycles per second, which from here on in are known as hertz. If you have 1 million of them, they're called a megahertz. If you have 1,000 of them, they're called a kilohertz. And it's not a coincidence. Radio, if anybody in the room still does listen to radio, you know, if you listen to whatever, if you listen to God, I can't remember now anymore. Whatever, if you listen to 104.3 megahertz on your FM dial, FM means frequency modulation. Modulate is to change. So you're changing the frequencies, and 104.3 on your FM dial means that something out there in space, which we'll get to, is vibrating at 104.3 million cycles per second. That's what it means. But now we can take it even one step. Lastly, okay, so I'm going to go on the very last page. I lied just to keep this clear. If we go like this, if we take the reciprocal of frequency, and this probably did come up in the lab, if you flip it, if instead of talking about cycles, if you flip frequency, instead of talking about cycles per second, if you talk about seconds per cycle, well, that's period, right? If I run 4 laps per hour around the track, that means that every one of my laps took me a quarter of an hour, right? Frequency is simply the literal, reciprocal, inverse, whatever you want to call it, of period. They are same information, just flipped, right? 1 over F is what is known as period. Period, capital T now, capital T. Like lowercase t is the independent variable time, but capital T means period, means literally the amount of time for one cycle. That's the thing you stress about usually in lab, or I mean, you focus on in lab, time for one cycle. That's the thing that we care about most in lab because it's the thing that's the most direct, it's the thing that we can directly measure and relate to, not coincidentally. Period, so in other words, period is time for one cycle. The units of period are seconds per cycle, or in other words, seconds. Right, so T equals 1 over F, which is to say T equals omega, which is to say, this is the other equation I was saying I was going to give you. A lot of people did use it already on homework 3, whether they understood it or not, wherever they got it or not. But now what I'm saying is, I just gave you 2 new equations in effect. I gave you that F equals omega over 2 pi, and I gave you that T equals 2 pi over omega. If you're following me, it's 3 different ways to track the exact same information. If you know one of the, so I'm saying, and this is where we're ending. Oh, sorry. Omega FT. They are 3 different ways of thinking about or tracking the exact same information. Literally, if you know one of the, and they're all constants for a harmonic oscillator. If you know one, you necessarily definitely know the other 2. You can figure them out from these equations that I just gave you, from definitions. They're all just rearrangements of the same idea. So the good news is, if you understand any of those, then I promise you, you shouldn't ultimately, don't be intimidated by the other 2. If you understand any one, you can always convert from the other 2 back to the one you understand. The reason we have 3 is just that. You're not alone if you're confused by any of them. All of us, for the most part, can relate to period the most easily. Period is just like, how much time does it take for the mass to go all the way there and come back? Or how much time does it take for the pendulum to go there and come back? Period T is just, what's the tick-tock rate? What's the amount of time for a tick or a tock? Like literally, because remember we said harmonic oscillators are all clocks. They're all just going back and forth at some steady rate that can't even be messed up, even if we mess up with the space of the oscillator. So the one that's easiest to measure in the lab, easiest to observe, easiest to picture in our mind is period, the last one. The one that is most directly emergent from the math is omega. Wait, so am I talking? I'm still here. Yeah, totally. Yes, I am. Omega. I'm sorry. Yes, I totally am talking about the frequency formula. I'm saying from here on in, all of you can convert fluidly, or can be expected to convert fluidly between omega, F, and T, between angular frequency, standard frequency, and period, because they're all just conversions of each other. Yeah, that. exactly. Yes, that's it in the direct chapter. Totally.
I had two things I wanted to say real quick. You're basically you're saying, first thing is you're saying that frequency is periods per second and period is seconds.
Yes.
Wait a minute.
Yeah.
Seconds per period.
Yeah. Frequency is
Seconds per cycle. Yeah. I keep on not knowing what to say because we're talking about periods, but different things have different periods. But we're saying the standard period is 2 pi. What do we say? The non-standard period, the micro period. What are we supposed to say when we're talking about?
Is every time your brain is about to say period, just say the word cycle instead, and that's and that's the thing for all this. Oh, sorry. Did you have another question? Sorry. Or do you?
Yeah. The other thing is every time I see this since like however many classes ago when I told you that the professor at lab showed us this, every time I look at it and like when I try to understand a little bit more, I keep getting reminded of like the basic equations for like uniform circular motion from physics 1. It seems so similar how everything converts back and forth, but it seems like it seems like there's something there, but I'm also missing something. It feels very similar, like it's almost the exact same thing.
Well, you're totally right. Everybody. And I'm going to say this. He's totally right. And it's 3-4. In 1 minute, anybody who has to go should go. And there's no insult. It's fine. But I'm going to answer this anyway. I'm going to hang out for a minute. You, Caleb, are totally, he's totally right. If any of this is familiar to anybody from uniform circular motion to physics, yes, it's the same thing. The only catch. And the reason that he keeps like using the language that he's using is what we're trying to do here is take the velocity issue out of it. When you saw this in physics 1 in uniform circular motion, you would have things like V equals 2 pi r over t. Like that's partly, I think, what Caleb's remembering correctly. You would have things like V equals 2 pi r over capital T. And then you would go from there to frequency and stuff. The thing is, in physics 1 at that time, we're trying to relate how fast something's going or how fast it's accelerating at any given instant to all these properties of the circle. What I'm saying now for the first time in physics, like the new level of this is we're trying to think of things that are going in circles or cycles without knowing anything about, we're trying to say now that the circle is a metaphor. From now on, something doesn't even have to be actually tracing out a circle in space for all this to apply. As long as it's cycling, then all these things still apply. So we're trying to come up with a way of talking about stuff where it doesn't matter whether a cycle is 2 pi radians on a cosine graph, or a cycle is mass there, mass back, or a cycle could even just be of a washing machine or something. We're trying to have a language that will relate to all cycles, no matter what shape they actually look like in actual space. So that's why it's totally similar to everything you said in physics 1, but it's also a little bit different because we're getting rid of the V and the A, and we're not even necessarily assuming anymore that there's literally a circle in space. We're now saying the circle is just cycle. Does that make sense? Or I don't. Oh, let me look at the chat. But again, okay. And anybody who's leaving, I mean, I'm just going to sit here for a second to make sure that settles. But goodbye. Okay, cool. Thank you guys. Yes, goodbye. Okay, and sorry, Caleb, you're saying that does.
Yeah. I see what you mean.
No, this is great. Well, thank you. Those are great questions. Honestly, or great insights. Everybody, again, goodbye. I mean, anybody who's goodbye. But anybody who's still here, like, I just hope everybody realizes I'm not just talking to one person. At any given moment, I'm trying to direct to one person because at any given moment, one is what it's about. But at any given moment, it could be any one, if that makes sense to people. But yeah, hopefully, okay. Thank you guys. All right, cool. And we'll talk more about the test tomorrow. And my battery's about to run out, I'm sure.
You have a test tomorrow?
Yeah. What?
Cool. We have a test tomorrow?
Oh, no. We'll talk about the test tomorrow. No. The test.
Oh.
No.
Okay.
No, you're good. No, the test will be posted Tuesday night. It will be over the weekend. No test tomorrow. We'll just talk more about it. But you're good. You would know. All right. Caleb, what school are you coming from, if you don't mind my asking?
VMCC.
Sweet.
Mm-hmm.
You know.
There's also, I wanted to say, like, homework 4, I just want to say, like, that it's starting to get fun, you know? That's when it's getting exciting.
Okay.
When we start, but that question that introduces the surface integral, where I had to realize that it's this, like, average radius, it's fun now.
Very good. Oh, you are. Wow. Oh, I wish we could go even far. Okay, so you need. I hear you. Well, I wish this course weren't so short. I wish we could really go into a lot of that stuff. But you did that.
Yeah.
Wait. So that means you are now John Jay? Like you were at BMC,
No.
you John Jay?
No. I just do too much on my own time. Since the beginning of the summer, have you ever heard of a book called Div Grad Curl and all that?
Oh yeah, I love
I've been
that.
studying that with my Calc 2 professor since the beginning of summer, so I'm almost through Calc 3. And I'm taking Calc 3 simultaneously right now, so it's like it prepped me for this and that, like electrostatics and Calc at the same time, you know?
Oh, that's great. That's a perfect book. Oh, we have stuff to talk about there.
For sure.
That's great. I'm so glad you know that book. That's one of my favorite books of all time. Oh, that's great.
Yeah.
Okay. Very good.
Mhm.
All right. All right. Anybody else? You guys are good. Antonio, Edie, Noelia. Thank you, Caleb. See you. See you.
See ya.
Yeah. You guys good? Everybody good? Noelia, Edie, you good? You guys good? Okay, I'm leaving. I'm going. Goodbye. Goodbye. 1, 2, 3, bye.